So last class, we started to have a conversation about this idea of average rate of change. And we talked about why rates of change are important, okay? But a rate of change is important because we're talking about the relationship between two changing quantities. Now, a really basic example is speed. Speed is a rate of change. We're talking about miles per hour, okay? So if an object is traveling in a straight line, the average velocity over a given time interval from t1 to t2 is defined as the change in the position divided by the change in time. And we've already started to explore this change in time last class because we talked about delta D over delta T, and that's exactly what's happening. I'm going to use the letter S, though, because S for position, okay? And that sounds kind of funky, but just go with it. So delta S over delta T, okay? Now, if S is a function, we're basically going to use our slope formula, and we're going to find S of T2 minus S of T1 over T2 minus T1, okay? So this is our basic way of finding average velocity, average rate of change, slope of the secant line. Now, a really basic example, if a car travels 200 miles in 4 hours, then its average velocity is going to be 50 miles per hour, change in distance over change in time. Now, that doesn't mean that it wasn't going faster or slower during that 4-hour period. It could have gone faster, it could have gone slower, but on average, its speed was 50 miles an hour. We talked about last class, if I was to walk to Mr. Modesty's room, it would take the time it took me to get there and the distance I traveled and divide them, okay? Now, it's important for you to know, we talked last class about instantaneous speed or instantaneous rate of change. We cannot define instantaneous velocity as a ratio because we would have to divide by a length of a time interval, which is 0. Now remember, we talked that in order to find slope, you need 2 points, but at an instant, you only have 1 point. So we talked about setting up a limit last class, and that limit making h, that distance between 2 points, as small as possible. But we can estimate instantaneous velocity and underline and highlight that word estimate by computing an average velocity over a super, super tiny interval and determining the limit as the average velocity, as lengths of time intervals get closer and closer and closer to 0. And I showed you this last class on that website where I was sliding those 2 points closer and closer together. So again, if I have this graph over here to the right where this is T1 and this is T2, if I was to connect those 2 points with a secant line, their slope of that secant line would be their average velocity, okay? Now, if we move this secant line so that T2 and T1 get closer and closer together, that secant line becomes closer to being a tangent line. And guys, this is not a new concept. We talked about this last class. The idea that if I can get these 2 points, T1 and T2, closer together, infinitesimally close, the closer I can get them together, the closer that slope of the secant line will be to the tangent line, okay? Now, slope of the tangent line at a single point is your instantaneous velocity. Now, guys, I know we're using velocity and speed a lot, but velocity is only one of the many examples of rate of change. Our same reasoning could apply to any quantity y that depends on a variable x, okay? So in general, when we talk about average rate of change, we talk about the change in y over the change in x. which is something you have seen since Algebra 1. In Big Kid Land, we say delta y over delta x. If we have a function, we're saying y of some x value minus y of some other x value over x2 minus x1, okay? So the instantaneous rate of change, we set it up by making a limit where we were scooting that x2 and that x1 closer and closer and closer together, such that the distance between them was almost zero, okay? Now, when you see an expression where you're talking about change in y over change in x, change in y over change in x, last class we called this a difference quotient. And it's super important that you know that on the AP exam, whenever you're finding a rate of change, you must show that you have used a difference quotient. You can't do that on a calculator and just put your answer. They want to see you set up a difference quotient, okay? So we're going to get to some definitions. And in general, when I put a box around something, that means you need to know it, and it's super important, okay? We're going to start to refer to the instantaneous rate of change as now a derivative. These two words mean the same thing and are interchangeable, okay? So what is a derivative? The definition of a derivative of some function at a point x equals c is going to be a limit of the difference quotients, okay? Now the symbol for derivative is f prime of x. It's like a apostrophe. It's not a number one. It's an apostrophe, f prime of x. And this is defined as the limit as h approaches 0 of f of x plus h minus f of x over h. And this should look familiar because we did this last class where x was an actual value. Now, if you have a limit of this thing, we say that f is differentiable at the point x equals c. Now, this definition of the derivative also has an alternate form. You need to know this as well. You could see the derivative written as f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. Both of these things mean derivative. You will hear me refer to the top one as the limit definition. You will hear me refer to the bottom one as the alternate form of the derivative. So what I want to do is do a really quick example with you and call it a day. So pretend a diver is jumping from a diving board that is 32 feet above the water. The position of that diver is modeled by this function. So I have a nice quadratic function. Now I can look at that and tell that my quadratic opens down. I can also tell that my y-intercept is 32. So imagine what that would look like here. It's going to start from a height of 32. He's going to jump up and down. Now you're not seeing the other part of this quadratic function because you would not have negative time. And here we have time and we have height. Okay, so we know that y sub 0 is 32. I can actually also find the x-intercept, this point right here. Okay, so if I wanted to find this point, I would need to set this thing equal to 0. And I would get everything positive by either moving it to the other side or multiplying by -1. Or I could even take out a -16. If I do that, I get t squared minus t plus 2. Ooh, excuse me, hang on. Minus 2. Okay, and that is factorable into t minus 2 then t plus 1, which gives me t equals 2 and t equals -1, which means this point over here is -1, and this point over here is +2. So my x-intercept is 2. So I have a nice picture to set this up for us. It says find the average velocity, aka the average rate of change, at which the diver is moving over this interval. Now this is not instantaneous velocity, this is average velocity. I'm talking about delta distance over delta time. So that means I need to find s of 1.5 minus s of 1 over 1.5 minus 1. Now guys, when you see this s of 1, remember that means we're going to be plugging into our function. What function? The function up here at the top. Okay, so we're plugging into that function. I want you to press pause on the video and go plug into that function real fast. Okay, so hopefully you got -24 feet per second. Remember, this is the average velocity over this time. That means if I was to start at 1 second to 1.5 seconds and create a secant line right there, that would be the slope of that secant line. And it's negative because he's obviously going down towards the ground. Okay? So now what I want to do is I want you to get out your calculator. Okay? And I want you to find the average velocity over these time intervals, which means you're basically going to do this exact same thing for 0.9 and 1, for 0.99 and 1, for 0.999 and 1. So you're going to use that same calculation you just did and find the average velocity. Now, I'm not going to do that on the video. I want you to do it. And what I hope that you see is that what I'm trying to do is sandwich you around the value of 1 and get infinitesimally close to 1 so that you can make an estimate of what the instantaneous rate of change would be at 1 based on some average velocities. So in your calculator, I want you to go find all of these average velocities using that delta D over delta T, and then I want you to make a guess as to what you think the instantaneous velocity is depending on your table, okay? And I'm going to check this as part of your video notes when you guys come back to class.